All right, so this is going to just continue on our definite integral journey and give you a little bit more context into some notation things and where we're going with this. So this notation here is a Riemann sum, and I want to connect it back to what we talked about in the very first video on definite integrals and where these things are all coming from. So what this notation is saying is for a function f of x, you're going to take some little subinterval that we'll call delta x. You're going to multiply that delta x by whichever function value you are going to do. So sometimes we'll do the left one, sometimes we'll do the right one, sometimes we'll do the one in the middle, but you're going to multiply by the output value that you have chosen. And by doing that, you're going to find the area of that rectangle. Now, this notation right here says, now add all of those up for as many rectangles you have chosen. So in this, if I chose to do 3 rectangles, then I would have f1 times delta x plus f2 times delta x plus f3 times delta x, and then that would end up approximating this area between the function and the x-axis using those 3 rectangles. Now, the more rectangles we take, the smaller delta x would end up being. So if I said, like, I want to do 6 instead, okay, I could do that. So I would have 6 of these calculations, and that's going to end up giving us a better estimate. In fact, if we let delta x get really, really, really ridiculously small, or if we let the number of rectangles go to infinity, both of these things meaning the same thing, then this summation gives us that smooth area that we want for a definite integral. So we can do these approximations in a couple different ways. Left endpoint method means that the function value that we are choosing is the left endpoint of the subinterval. Right endpoint method means that we're using the right endpoint of that subinterval. And then I'll also show you an example with midpoint method and what that means. All right, let's go ahead and look at an example here together. Using both left and right endpoints, let's approximate the area under the curve of f of x equals x squared from 0 to 2. And then it says n equals 4. So with 4 rectangles, I'm going to go ahead and draw this pretty big over here. Here's 1, here's 2. I'm going to be at 0, 0, 1, 2, 3, and 4. 1, 1, 2, 4 are my points on my parabola. Oh goodness, that was not a very good graph. That's okay though. Okay, so I need to make this 4 rectangles. So that our delta x is to do the difference in my subinterval, or my total interval, I should say, and then divide that by 4. Because I need to divide that number line up into 4 equal pieces. So my delta x is going to be a half, which makes sense. And then if I'm going to use left endpoint method, then I'm going to look at my first subinterval from 0 to 1/2. Well, I'm going to use 0 as my f of x value. So I would do 0. Well, let's write it out first. F of 0 times a half. And then my next one is going to be f of 1/2 times 1/2. My next subinterval, the left endpoint between 1 and 3/2 is 1. So I'm going to say f of 1 times 1/2. And then my left endpoint of my last subinterval is 3/2. So f of 3/2 times 1/2. All right, and then I'm going to put this in a calculator to find. So let me go ahead and pull up my Desmos. I'm going to say f of x equals x squared, just to kind of show you a way to do this. And so that way I can plug in what I just put in my function notation, and it will recognize that. And that way I can put in 3/2 if I want to, or whatever. All right, so it says my area is 1.75. All right, I'm going to go ahead and keep this all here, but I'm going to change my pen color. Let's do a blue. There. Sorry, I probably moved the screen around a lot for you. Okay, so let's do right endpoint method using the same graph. So all of my delta x's are all going to stay the same because I'm using the same number of rectangles, but now I'm going to use the right endpoint in order to figure out what my f of x value should be, or the height approximation should be. So right here, I'm going to use that right endpoint in the subinterval. So this is going to be f of 1/2 times 1/2. My right endpoint of my next subinterval would be 1, so I'm going to use f of 1 times 1/2. I'm going to use f of 3/2 times 1/2. And then this one I need to use f of 2. Okay, so in the right endpoint method for each subinterval, like 3/2 would be the left endpoint, 2 would be the right endpoint. So I need to use the function output at f of 2. That's going to be my height for my rectangle, and then my base is still 1/2. All right, let's go in here. Now the nice thing about entering it this way is I can just go in and say, like, I don't want, which is 0, but I just don't want this one anymore. And I need to add to this f of 2 times 0.5, and that gives me 3.75. Now, as you can see by the area, 1.75 is a little bit too low. 3.75 is a little bit too high. You can average these and be like, I bet it's 2.75. And that's another way that you can kind of approximate this even better. Or I could use different rectangles, or smaller size rectangles, more rectangles is what I should say. And then another thing we can do is use the midpoint. So if the left is too small and the right is too big, maybe if we use what we call the midpoint, we could get a better approximation here. So I'm going to keep the same graph, and I'm going to change my color just one more time here. And we're going to do midpoint method. Now in here, I'm still using n equals 4. So my delta x value is still going to be 1/2, but I'm going to use the midpoint of the subinterval for my f value. So the number between 0 and 1/2 is 1/4. So I'm going to use f of 1/4 and multiply by 1/2. So I'm going to say that that's the height of the rectangle. Okay, f of 3/4 to define that height. F of 5/4 to get that height, and f of 7/4 to get that height. All right, let's go into our calculator and see. Oh, oops, I didn't mean to do that. That's okay. F of 1/4 times 0.5 plus F of, we said 3/4 times 0.5. I wonder if this is going to cause an issue. Let me erase that. There we go. F of 5/4 times 0.5 and F of 7/4 times 0.5. All right, and that looks like it's 2.625, which is probably a better estimate of the actual area. All right, let's look at another type of example. Now here is the formal definition from the textbook about a definite integral. Again, we're going to take infinite number of rectangles, and in class I'll kind of show you a demonstration, probably actually before you watch this video, of kind of where we're going with this. It's also important to realize that we don't have to use x. I know we normally use like x and y for our stuff, so we're used to saying like change in y over change in x, or we called that dx for delta x, but it doesn't have to be x. Like we could say f of t dt or f of u du. All that little piece here says is like, that's my independent variable. Okay, that's what's on that like x-axis, and then I'm taking those function values to find my area pieces and adding them all up. All right, let's look at this example here. So evaluate this integral 0 to 3 of that function, square root of 9 minus x squared. Let's look at what a graph of that would be. I'm going to go ahead and get these out. F of x equals the square root 9 minus x squared. So I have a semicircle, radius of 3. And so one thing that is true about this that isn't true about any of the other ones that we've looked at is this is a known geometric shape, right? So if we go back here and draw ourselves a graph from 0 to 3, I'm looking at the quarter circle. And again, this notation means find the area between that function and the x-axis from 0 to 3. So if I have a radius of 3 and the area of a full circle is pi r squared, then this piece of that circle would be a fourth of that, right? If you had like the whole thing around. And so this area is going to be 1/4 pi and then 9, so 9 pi over 4. And so it's possible that you might still need to find areas of known shapes, okay, from geometry in order to find these areas. And the big connection is that this notation means find the area, find all of those heights over that interval, multiply them by their dx's, and figure out what that area would be.